We're on our last problem for the practice final, and this is on exam 2 concepts, so tensors, circles, and graphs. So again, mechanics problem most likely, maybe a little bit thrown in with some strengthening mechanisms, but let's go through this example problem. So I had a pipe burst in my house earlier this semester. I was using a copper pipe, so we were instead of the new PEX piping, which is much more ductile. So copper, so I know that I'm using copper, so I know that's a metal. So I'm going to estimate that the Young's modulus is approximately 100 gigapascals, 100 GPa. I know my Poisson's ratio for metal is 0.3. The pipe was approximately 0.1 meters in diameter, so the radius is equal to 0.5 meter. That's my radius. And it is 5 millimeters thick. So thickness equals 5 times 10 to the minus 3 meters. Below is a schematic of the fracture surface that I observed in my pipe. So let's actually go ahead and I'm going to label this as my axes. So along the kind of, basically the circumference or circumferential, and then along this direction. So I'm going to label this as y1, y2. I know that this is going to be basically this is your longitudinal direction, this is your hoop direction. So according to San Joaquin water, the pipe should have been pressurized at 1 megapascal. So delta P theory should be approximately 1 times 10 to the 6 pascals. However, my pipe burst at a strain value of 12%. So first, let's go ahead and start to plug in some values. So when we hear radius and we hear thickness, what do? Well, we go ahead and make sure, are we a thin-walled pressure vessel? So remember, if we're a thin-walled pressure vessel, R over T is greater than or equal to 10. If that's the case, we know that our stress tensor is just going to be this. Sigma, in this notation, sigma L, sigma hoop. Everything else is 0. Here, and I know also that my strain tensor will be strain in L, strain in hoop, 0, 0, 0, 0, 0, 0, 0. And I also know that my sigma hoop is equal to delta P R over T. My sigma L is going to be half of that, 2. And I could even go a step further and start to kind of write out that my hoop strain is going to be equal to 1 over E times sigma hoop minus nu times sigma L. And the longitudinal strain is going to be 1 over E times sigma L minus nu sigma. So let's actually see what the first question is asking. So is my fracture schematic correct? Why or why not? So we've just proven or shown here that the hoop stress is twice as large as the longitudinal stress. So if I'm pulling in the hoop direction, which is basically pulling up like here and here, is our fracture schematic correct? Yeah, because if you're pulling a material here and here, it should fracture transversely. If the stress was larger pulling here and here, you'd see a fracture surface like this, basically perpendicular or transverse. So the fracture surface is correct, and then that's kind of the reason now. So determine the stress and strain tensors quantitatively. What was the real pressure in my pipe? Do we believe that San Joaquin Water County? Draw the 3D Mohr circle for the stress state, and what if the stress rate was 17 degrees counterclockwise from the maximum shear stress state? So let's go ahead and tackle this one by one. So first, it says my pipe burst at a strain value of 12%. So we know that it's going to burst first at the largest strain, largest stress. So that is going to be 0.12. That's going to be my hoop stress. So now let's go ahead and actually go back all the way to lecture 7 for a second, because I know that I'm going to have to rotate my stress state. So I am going to use my old friend, which is my linear algebra. I'm going to define this real quick. So my T matrix is going to be equal to, again, C squared, S squared, 2 times S times C. So you're probably sick of this at this point. Hopefully you have this already defined in your notebook. 2 times S times C, and minus S times C, and C squared minus S squared. There we go. I'm going to go above here. C equals cosine of theta degree. I'm going to be degree mode. And I'm going to do S. Oops. That. Get rid of this guy like that. S equals sine of theta in degree. Close it up. Define that. And we can look at it a little bit larger now. Let's actually pull it up on the side here. So I'm going to do P matrix form. So we can see our matrix or rotation there. All right, so we need to go back, and let's go back to our problem. So we were trying to figure out the stress and strain tensors, which we've already written quantitatively. So what are our unknowns in this problem? Well, we know R, we know T. We don't know what the real delta P is. We don't know sigma H, but once we have delta P, we'll have sigma H, we'll have sigma L. And we know what EH is. That's already defined. Now we just need to figure out what is EL. So let's start to define and figure out and solve these equations. So first, actually, if we just solve for delta P, we can figure out everything else. So all I'm going to solve is, I know my EH, so let me just define sig H is equal to, let me define my radius. So radius equals 0.05. My T, actually let's confirm that my R over T is greater than or equal to 10. 5 times 10 to the minus 3. So let's do R divided by T. Good. Greater than or equal to 10, we're good to go now. So sig H equals del P times R divided by T. I know that my sig L equals sig H divided by 2. So we're good to go there. So now I just need to solve. I know also, actually, let me write my Young's modulus equals 100 gigapascals, 10 to the 9th. I know my nu is equal to 0.3. So now I can solve that 0.12 is equal to my material failed at a strain, and we know that it will fail at hoop strain first. 1 over y, my Young's modulus, times sig H minus nu times sig L. I'm going to solve for del P. That's it. So this is my delta P. So I'm going to copy this, say del P equals this. So now I could do my stress equals, it was sig L, 0, 0, 0 sig H, 0, and 0, 0, 0. So stress, matrix form. There's my stress tensor. Now let's do my strain is equal to EL, 0, 0, 0, EH, 0, and 0, 0, 0 here. And we know that EH was equal to, right before fracture, this. EL equals 1 divided by y times sig L minus nu times sig H. Should I solve that one correctly up there? Yep. Here. So now I have to look at my strain matrix form. There it is. So I've got my strain values, my strain tensor, I've got my stress tensor quantitatively. We know my delta P was actually 1.4 times 10 to the 9th, so way higher than that theoretical value here. So we found the real pressure. We determined the stress strain tensors quantitatively. Draw the 3D Mohr circle for this stress state? Well, we know for this stress state, we're already in the principal kind of Mohr circle stress state. So your 3D Mohr circle for any thin walled pressure vessel, if you're in that kind of initial stress state, so if I do my tau sigma, I have sigma H is larger than sigma L and 0. So I have a circle here. Excuse me. Let me undo that. Undo. So I have a circle that goes through here, a circle goes through here, and a circle connects 0 and 0. That's it. That's my 3D Mohr circle. Now it says, what is the stress state 17 degrees clockwise from the maximum shear stress state? So the maximum shear stress state occurs at an angle of basically a theta of 45 or a 2 theta of 90. So at that rotation, if I'm going from here to here, I'm going counterclockwise 45. And then now if I go, what is the stress state? 17 degrees from that maximum stress state, I'm doing 45 minus 17 degrees. So that is what I'm going to kind of dot into my stress tensor, or my T matrix right here. So if I want to do my T matrix dot stress dot transpose T matrix, and I'm going to do slash dot theta goes to 45 minus 17. I'm going to define, because my 45 initially was positive, then clockwise is negative. Let me do matrix form. That's it. That's my answer for this problem. So that's it. We're done with the exam. So again, if you have any questions, please let me know. Thanks for watching the videos, and I'll see you in other classes. Congratulations, you're finished with ENGR 45. Good luck on the exam. Thanks. Bye.